Hello, and welcome to Big Data Hadoop and Spark Developer course offered by Simplilearn. This lesson is an introduction to Big Data and Hadoop ecosystem. Now, what you will learn in this session. After completing this lesson, you should be able to first understand the concepts of big data and its challenges, explain Hadoop and how it addresses those challenges, and finally, you should be able to describe the Hadoop ecosystem. In the first topic of this lesson, you will get an overview of big data and Hadoop. So first, let's look at the evolution of big data. Before the year 2000, the data volumes in our databases tended to be relatively small compared to what they are currently. However, the processing was still fairly complex, and all the computations were dependent on a single server or a small cluster of database servers. And as the volume of the data grew, we needed to upgrade the server, add more processors or add more memory. However, after the year 2000, we saw the data explosion, and our single server hardware was no longer keeping up with the growth of the data. Now, let's look at the data explosion that happened in the recent decade and a half. Back in 2012, IBM reported that 2.5 exabytes of data, that's 2.5 billion gigabytes, was generated every day. And that was in the year 2012. Now, looking at more recent statistics, that's reported by Forbes last year. 40,000 search queries were performed by Google every second. Up to 300 hours of video are being uploaded to YouTube every minute. In Facebook, 31.25 million messages are sent by the users, and 2.75 million videos are viewed every minute. A year ago, they estimated that by now, 80% of all photos will be taken by smartphones, and by year 2020, at least a third of all data will pass through cloud. And about 1.7 megabytes of new data will be created every second for every human being on the planet. So that's the scope of the data explosion that we saw in the past decade and a half. So what's the solution for managing this enormous volume of data? And the solution is with distributed systems. So instead of a single large server, we can have lots and lots of machines connected together in a cluster and sharing the workload. And that's what is called a distributed system. Now let's look how distributed system works. Let's consider an example. Suppose we have a single machine that has 4 I/O channels, and the speed of each channels is 100 MB per second. So if we want to process 1 terabyte of data, that will take us 45 minutes. Now, if we have a 100 machine cluster connected together, it will take only 45 seconds to solve the same problem. So that's how distributed systems help us process big data. So next, let's look at the challenges faced by big data systems. One is the high chances of system failure. If we have lots and lots of machines connected together in a cluster, if one machine fails, that can bring down the whole cluster. Second is the limit on the bandwidth, because all those machines need to be connected together on a network. And finally, high complexity of programming, because now what we not only have to worry about solving the problem at hand, but also have to manage all those machines on the cluster that have to be synchronized and work together. Now, Hadoop is the platform that was designed specifically to address those challenges. What is Hadoop? Now, Hadoop, the official definition, Hadoop is a framework that allows for distributed processing of large data sets across clusters of commodity computers using simple programming models. Originally, the platform was inspired by a technical document published by Google years ago. The word Hadoop by itself does not really have any meaning. Doug Cutting, one of the original developers of Hadoop, named the system after his son's toy yellow elephant. So that's how the name came about. Let's look at the key characteristics of Hadoop platform. There are 4 of them. Hadoop is reliable, scalable, flexible, and economical. Now, it is reliable because every piece of data in Hadoop clustered is redundant and is copied across multiple machines in the cluster. So if one machine goes down, the data will still be available and the cluster will continue functioning. It is economical because Hadoop runs on the cluster of commodity hardware machines. There is no specialized hardware involved. It's all cheap machines. The reason Hadoop is scalable is because in order to scale it both horizontally and vertically, all you need to do is just plug in additional nodes into the cluster. And it is flexible because it can store virtually unlimited volumes of data, and it can handle both structured and unstructured data. So those are the key Hadoop characteristics. Next, let's compare Hadoop to traditional RDBMS platforms. Let's consider an analogy. Let's compare dining habits of humans and tigers. So as humans, in order to consume our food, we bring it into our home, we cook it, we serve it, and then use utensils to bring food to the mouth. Now, tiger, on the other hand, tiger brings his mouth to the food. So if we look at traditional database platforms versus Hadoop, in traditional platforms, in order for data to be processed, it has to be retrieved from the disk, from storage, and then pulled into the centralized processing engine. And that single processing module becomes a bottleneck. While with Hadoop, what happens is that the data processing program itself is sent to wherever data is located. So that's the revolutionary idea behind the Hadoop platform. So next, let's take a look at several use cases of Hadoop and see what similarities and what common trends we can find. First use case is a bank using risk modeling. So originally, a bank had multiple data warehouses, one for each department, and each one performed its own risk analysis. Now, after bringing in Hadoop, the company was able to combine all their data on a single platform and run more reliable risk analytics and produce better models. Another example is a recommendation engine for online dating. Now, the challenge here is if we look at database problems we solve in a traditional database world, we would usually have a single item compared to a large data set across one or maybe a handful of parameters. Here, if you think about online dating recommendation engine, you basically have to compare everyone to everyone across lots of different parameters. So that is a big processing challenge. Another example, threat analysis. So let's say a company wants to monitor for criminal behavior like theft, fraud, and abuse. So the challenge here is that a single event by itself may not be meaningful and indicative of anything in particular. It is when we identify a trend, when we identify multiple similar events or dependent events, then they become meaningful. Another example, let's say a company wants to measure public perception of their organization. And for that purpose, they monitor multiple social media platforms and continually monitor each of those for opinions being expressed online and ranks it as positive, negative, or neutral. So one of the challenges here is streaming data and streaming simultaneously from multiple sources. Another example is search quality, something like a search engine. Here you have to examine and rank an enormous volume of data, lots and lots of material published online, and which you need to analyze and rank in order to optimize user search. To that, I can also add an example from my own recent practice. I am building a product for a healthcare client, which would allow them to measure and compare the quality of healthcare. So here the challenge is that the data for millions of patients need to be combined from multiple sources, and complex statistical algorithms need to be applied in order to calculate the common quality measures and compare them to each other. So next, let's briefly look at the core components of Hadoop. Later, we'll examine each of them in more detail. First one is Hadoop HDFS, which stands for Hadoop Distributed File System. So that's the storage component of Hadoop. That's where your data is stored. Next is Yarn. Yarn happens to stand for Yet Another Resource Navigator, and that's basically Hadoop's resource manager. That's the component that allows you to coordinate jobs and tasks that are spread among the many machines in the cluster. And finally, the processing components, which are Hadoop MapReduce and Spark, where MapReduce is the original processing engine and Spark is becoming more popular in recent years. We'll cover each of these components in more detail in the later in the class. So next topic, introduction to big data and of introduction to big data and Hadoop lesson is Hadoop Ecosystem. Hadoop has an ecosystem that has evolved from the three core components that we've just discussed: processing, resource management, and storage. So on this topic, we will learn about each of those components and how they work together as a single ecosystem. So looking at Hadoop's core components, HDFS, which we already covered, distributed file system. Now, the data that resides on Hadoop can reside either in raw files on HDFS, or it can be stored in one of several NoSQL databases. One of them is HBase, and we'll cover it later in more detail. Yarn we already briefly covered, which is the resource manager, and the data processing agents, MapReduce and Spark. Now, before the data gets into Hadoop, before it's stored on the distributed file system, data needs to be ingested from somewhere. So we'll cover two of the data ingestion options available in Hadoop, which is Scoop and Flume. Next, we'll explore the tools that are available to us for analytics, and those are Pig, Hive, and Impala. And we'll also cover data exploration and end-user tools like Hue and Cloudera Search. And finally, we'll briefly talk about Uzi, which is a workflow manager that helps us manage complex workflows. So next, let's discuss in some detail HDFS, Hadoop Distributed File System. So it is a storage layer of Hadoop. It's suitable for distributed storage and processing, and data can be either stored there raw or in NoSQL database platforms. Now, before the data is written to the file system, it gets automatically distributed. So any piece of data that is ingested into Hadoop gets distributed across all available nodes in the cluster, and that process happens automatically. But to you as a user, this process is entirely transparent, and you communicate with HDFS via a command interface. It looks just like any regular file system. HDFS provides streaming access to file system data, and it supports the authentication and file permissions just like any other file system would. So how is data stored in HDFS? One option is to store data in HBase, which is a NoSQL database. In other words, it's a non-relational database where no in NoSQL stands for not only SQL. HBase is used to provide random real-time read and write access to big data, and it provides support for high volume and high throughput. Being a NoSQL database, a single HBase table may have thousands of columns. It is more of a logical structure, which is not directly related to how the data is actually stored underneath. So, data ingestion tools. One of the popular data ingestion tools is Scoop. And Scoop is designed to transfer data between Hadoop and relational databases like Oracle, SQL Server, MySQL, and so forth. And Scoop works is bidirectional. You can use it either to ingest data into Hadoop or to export data from Hadoop to relational databases. Flume is another option for data ingestion. Uh, it works very similar to Scoop. Main advantage of Flume is that it is suitable for streaming data. So that's what it's ideal for. Let's talk about Spark. So Spark is a cluster-based computing framework, and it is extremely fast. It can provide up to 100 times faster performance than MapReduce-based framework. And what makes Spark so exceptionally fast is that it works exclusively in memory. There is no disk storage in Spark, so there is no retrieval from disk step when you use Spark for analysis. Spark supports machine learning, business intelligence, streaming, and batch processing. The components of Spark are core and resilient distributed data sets, or RDDs, Spark SQL. Spark does support SQL, Spark streaming, machine learning, and GraphX. In addition to SQL, by the way, Scala is a very popular option with Spark. That's what we are, by the way, using in our current project. It is a similar framework to SQL, but it is a lot more flexible. MapReduce. So MapReduce is another option for a processing framework, and this is actually the original framework that came with Hadoop, and it is a Java-based framework, and it works as a map and reduce paradigm. Those are basically Java-based, fairly sophisticated programs. Many Hadoop tools like Hive and Pig are built on top of MapReduce, so they basically provide a simpler interface into MapReduce, and we'll cover those tools later in the course. So now that we covered the processing component, let's talk about components that can be used for data analysis. One of them is Pig, and Pig is a scripting interface on top of MapReduce. Now, the advantage of Pig is that it's much simpler. MapReduce programs can be quite voluminous, can include hundreds of lines of code, while Pig allows you to perform your task with a fairly simple scripting interface. And simple commands like filter and join can take a lot of code with Java-based MapReduce, but just a few lines with Pig. Now, Impala, another option we can use for analytics. Now, Impala is a SQL-based framework. It is used as a dialect of SQL, and the main advantage of it is that SQL is familiar to most database developers. With Impala, you have very, very low latency. It can support multiple users, and it provides a high performance SQL. Another option is Hive. So just like Impala, Hive is also a SQL-based framework. It's not as fast as Impala, but it does provide better support for SQL. It supports a lot more SQL operations than Impala does. Now, it is similar to Pig in a way that it is also an interface on top of MapReduce. So whenever you create a SQL statement in Hive, when you submit it, it gets translated into a MapReduce job and then executed. So it is a two-step process, which makes it slower than Impala, but it is more flexible. And Hive is typically used for batch processing, like ETL jobs. So next, we'll talk about data access tools. One of them is Cloudera Search. It comes packaged with Cloudera distribution of Hadoop, and it works against true HDFS files, or you can use it against data stored in HBase. Cloudera Search enables non-technical users to search data available in Hadoop. So it requires no programming skills. It's very simple, intuitive interface. Next component we'll discuss is Oozie. Oozie is a workflow manager and a coordination system that is used to manage Hadoop jobs. When you have complex tasks that need to be built into workflows, when you need to manage dependencies, that's what Oozie is used for. It creates workflows so that the tasks are well managed and your processes do not step on each other's toes, so to speak. So that's what Oozie is used for. And finally, Hue. Now, Hue is stands for Hadoop User Interface. And one way to describe it, it's really a portal into the Hadoop world. It's a web-based interface, and through it you can access all tools and all resources available in Hadoop. You can use it to execute queries in Hive or in Impala. You can run Pig jobs or Spark processing jobs. You can search data. So it's basically your single window into the Hadoop world where you can access all of the available resources. So to cover what we just learned, the 4 stages of data processing in Hadoop. It's data ingestion, processing, analysis, and access. So for ingestion, we've covered scoop and flume. For data processing, we talked about HDFS, Hadoop Distributed File System. We've covered HBase, one of the NoSQL databases available in Hadoop. We've talked about MapReduce and Spark, where MapReduce is the original processing agent, and Spark, a much faster memory-based processing framework that's becoming more and more popular in the recent years. We discussed several options of analytical tools that can be used in Hadoop. To remind you, Hive and Pig are the interfaces that sit on top of MapReduce, where Pig provides a scripting interface and Hive provides a SQL interface. We also covered Impala, which is another way to access Hadoop via SQL. The main difference with Impala is that instead of translating SQL into MapReduce jobs, Impala goes directly to the data, and that makes it work much faster, although Hive is more flexible as it supports more SQL features. And Hive would typically be used for ETL jobs, while you can use Impala for real-time data access. And finally, we've also discussed end-user access tools like Cloudera Search, which allows you to search data available in Hadoop, and Hue, the portal into Hadoop that allows you to access any tool and any resource available in Hadoop. So let's look at the key takeovers, what you should be taking out of this class. Let's go over the key points. First, Hadoop is a framework for distributed storage and processing. Core components of Hadoop include HDFS for storage and Yarn for cluster resource management, and MapReduce or Spark for processing. Hadoop ecosystem includes multiple components which support each stage of the big data processing. Flume and Scoop to ingest data, HDFS and HBase to store data, Spark and MapReduce to process data, Pick, Hive, and Impala for analysis. Hue and Search you can use to explore the data, and Uzi to manage the workflow of your Hadoop jobs. So that concludes our lesson.